So in this video, I want to introduce the idea of talking about linear systems. In other words, systems of linear equations. So what we've seen so far is we've been given some linear ordinary differential equation. Maybe it's a second order homogeneous or a first order linear or whatever. We've been given some sort of an equation. We have to solve it and we have to figure out what's the function that satisfies that. This is slightly different. So here when we're talking about linear systems, what we're doing is we have two equations that are describing something, and then we want to find a solution. So a solution usually means a set of solutions, say x and y, that satisfy both equations at the same time. Okay, and so there's some interpretations of that. So the first example of this that I want to talk about is what's called the Lotka-Volterra system. So this is what's used in um, ecology to study predator and prey. This is one of the ecological models that gets used. And the idea is that you have, say, predators and prey, and we're just ignoring everything else except for the predators and prey. So we're assuming that there's only two animals in the world, or maybe there's only two animals in this certain like field, whatever. And we're just going to think about the interactions there. And then here I'm going to let x be the number of predators that we have and y the number of prey. So if you want to think of x as like the number of foxes and y as the number of rabbits or something like that, that's totally fine. And the way that this works is, let's just go through one by one and think about the terms. So dx dt is the rate of change of the predators. And the idea here is that if y is 0, if there's no prey, then the predators are just going to die off exponentially. So that's why you have this exponential decay term here, dx dt equals minus ax. However, if there is prey, then what's going to happen is that the rate of change of the predators is going to be proportional to the number of interactions between the predator and prey. So remember that if there's x predators and y prey, then x times y is the number of interactions between the two groups. Okay, so it'll be proportional to that. On the other hand, think about this from the prey perspective. If x is 0, if there's no predators, then the rabbits are just going to, the population of the rabbits is just going to expand exponentially. So it's going to grow proportional to its health. On the other hand, if there are predators, then the main term here, the dominant term, will be the minus dxy, and the death rate is going to be proportional, again, to the number of interactions between the predators and the prey. Okay, and so this is the Lotka-Volterra model. This is a kind of complicated system to solve explicitly. And so one of the things that often gets done with these is, instead of looking for an actual system, what you can do is you can plug in a few starting values, pick a few constants A, B, C, and D, and then kind of let this run, kind of let a simulation run, see what's going to happen. See if maybe what's going to happen is, over time, there's going to be like a loop, right? So if the number of predators increases, that's going to decrease the number of prey, which is going to decrease the number of predators, which will increase the number of prey, and so on. And you get kind of an infinite loop in that way. So if things are balanced nicely, that happens. Otherwise, what can happen is that things might actually stabilize. So maybe things kind of move one way or another, and then things kind of equalize. So there's an equilibrium point, so that there's an exact right number of predators and prey for everyone to live in balance. Okay, and so you can study these systems. Now, the systems that we're going to study, so this is a slight misnomer here. What I have here is not a linear system. So we're going to start by talking about systems of ODEs, like this Lotka-Volterra model. One other model that I just wanted to mention before I forget is what's called the SIR model. And this is a model that gets used in epidemiology. And this is a model that's being very useful right now in the middle of the coronavirus pandemic. So that's very useful. And this is a model that measures the susceptible, okay, which is in other words, the population that's at risk for getting the disease, the infected, which is the population that has the disease, and then the recovered. Okay, and so this is why it's called the SIR model. And it's a pretty complicated nonlinear model. You're not going to be able to solve it explicitly. But when you graph things, it actually turns out that when you graph things, you get the nice shapes of all the coronavirus curves that you have. So the curves are nice, obviously, not the coronavirus, but you get the nice shapes of the graphs that you see from time to time on the news or on different statistical models when you're talking about the coronavirus pandemic. So this can at least explain some of the shapes of that. Also, coincidentally, the SIR model is the picture that you see on our course when you log into WebAssign. So if you've ever wondered what that picture is, that's a picture of the SIR model. And it's, you pick some starting parameters and then you let it run, and then it turns out that that's what the curves look like. So that's the SIR model. What I want to do, and what we're going to do in this chapter, is we're going to solve linear systems. Okay, so we're going to look at linear systems. In linear systems are where you have, say, 2 or maybe even 3 equations. There's no reason why you have to limit yourself to 2. So the SIR model already has 3 populations in it. But we're going to look at linear systems. So this is going to be things like x is ax plus, dx dt, I mean, is ax plus by, and dy dt is cx plus dy. And what we're going to do is just some perfectly straightforward computation. There's some fancy stuff that you can do with these linear systems. So anytime you see anything that's linear, linear algebra is probably hanging out somewhere in the background. So if you've ever seen some linear algebra or taken a linear algebra course, there's definitely some matrix methods that you can do here. I do not assume that everyone has had linear algebra. And so we're not going to go over that. I'll just show you how to do some of these by hand. Okay, so in the next video, we'll talk about some examples.